Algebra 2, Chapter 6.2, Graphing Polynomial Functions. Essential question, how do you sketch the graph of a polynomial function in intercept form? I call that sometimes factored form. And we have the teaks right to move range function interval notation. And this is from the book, Explore 1, Investigating the End Behavior of the Graphs of Simple Polynomial Functions. And we start out here by talking about the standard form, or general form of a polynomial equation, and this is it right here. And what we have is we have each term that has a raised to a certain power, and then these numbers in front of each of these terms, which are with the x variables, is called a coefficient of each of these terms. And then a polynomial function of degree 4 is called a quartic function, x to the 4th power. That would be x to the 4th power. If you see a leading term, the highest power, x to the 4th, quartic. If you see a function of degree 5, and what is degree 5? X to the 5th power, the highest power term. We call that a quintic function. And if we have after degree 5, polynomial functions are generally referred to by their degree, or as in 6th degree polynomial function. So just a little vocabulary. Next, A, use graph calculator to graph the polynomial function f of x equals x, f of x equals x squared, f of x equals x cubed, and so on. And it says use a graph of each function to determine the function's domain, range, and behavior. I'm going to just graph a couple of these. And I'm going to graph the ones that you probably haven't already known too well. I'm going to start with x to the 4th power. And go x to the power 4. And the graph. And we have what looks kind of like a parabola, but this parabola is smashed flatter against the origin of the x-axis. Let's go to x to the 4th here. Domain, the domain of this polynomial function in all polynomial functions is all real numbers, which I can note right is greater than negative infinity, less than infinity. And that is likewise going to be the case for all of these. So I'm just writing them in. Negative infinity, negative infinity, less than infinity, negative infinity, less than infinity, and then the last one. Okay, next, the next column here is range. And we are starting out here with the x to the 4th graphed. And what we see here is, looking back at our graph, we have a minimum of 0 where x equals 0. So the value function never goes below 0. And so our range is going to be this one, the interval notation. We're going from greater than or equal to 0 all the way to less than infinity. And let me go ahead and take x to the 5th power, and we'll examine that quickly. If we go to x to the 5th power, go right here, change that to 5th power, graph. Okay, here we see the graph looks like a cubic function, comes up, touches the origin, and then continues to go up after touching the x-axis. And so in this case, our range is going to be all real numbers. So we're going to put down for x to the 5th power, our range in this case is the same as the range. And what we have for any odd-powered function, we have the similar situation. So if you look at our parent function of linear function f(x) equals x, our range is also going to be greater than negative infinity, less than infinity. Our quadratic function is going to have a minimum of 0, and so we're going to go our range from greater than or equal to 0 to less than infinity. And then for x to the third power, we have the range greater than negative infinity, less than infinity. And then for down here, we have the sixth power. We have greater than or equal to 0 and less than infinity. And then the last column we have is end behavior for a linear function. And a linear function, I'm going to just sketch it here. Our linear parent function looks like this. And as x approaches infinity, f of x goes up, approaches infinity. As f of x approaches negative infinity, f of x approaches negative infinity. And it's going to be likewise for x to the third power, and then we have x to the fifth power, so what we have for x to the first power, x to the third power, x to the fifth power, these end behaviors are all the same. Now next, we have f(x) equals x squared, and this is what that one's going to look like. I'm sketching it right here. Okay, as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches infinity. And it's going to be likewise for all of these even-numbered functions. I haven't talked about that much. So that's going to be it. So this really builds upon what we did at the beginning of the year, where we talked about the basic pair functions of 2, which included our linear function, our quadratic function, and our cubic function. Next, B, use graph calculator to graph polynomial function f(x) equals negative x, negative x squared f(x) equals negative x cubed, and so on. These are going to be very similar to the last one. I'm not going to go over all these. Well, I'll go over this negative x cubed. Just graph that really quickly. If we go to negative x cubed, this is what that looks like. So we're starting high and ending low, but our domain and range are still all the numbers. So just writing that out quickly, we have our domain greater than negative infinity, less than infinity. Our range is the same, greater than negative infinity, less than infinity. As far as end behavior, as f of x approaches positivity, f of x approaches negative infinity because we are going down. And then as we go the other direction, as x approaches negative infinity, f of x approaches infinity. So if we turned over back to part A, we would see just the opposite in behavior-wise. And then just to do one of these, if we have the negative x to the fourth power, we still have our domain is going to be greater than negative infinity, less than infinity. But in this case, going back to the graph, we go up here, x to the fourth power, and we should see that we have a maximum of 0. And so in this case, our range is going to be greater than negative infinity, up to 0. And we bracket that off. And then our end behavior as x approaches infinity, fx approaches negative infinity. So you're going down as you go to the right. As you go to the left, as x approaches negative, fx also approaches negative infinity. And then you go and fill in the rest of these. Next, how can you generalize the results? I'm not going to go there. And now we'll talk about turning points, x-intercepts and turning points. And so you get some technical language. I'm going to go with my turning points is where the function will change from increasing to decreasing, or from decreasing to increasing. And x-intercepts would be where the graph function touches or crosses the x-axis. Okay, now, using graph calculator, graph cubic functions, and we have these cubic functions, and we're given 3 varieties. I'm going to go ahead and do the first one, f of x equals x cubed. So if we go here, clear this, put x cubed, and we graph that function. Remember what that looks like. How many distinct factors does f of x have? Well, only one, because what we have is x cubed, which is x times x times x. And so we only have one factor 3 times. So our answer to this one is 1. One of the graph's x-intercept, so it's going to be at the origin. So we have 0, 0 is going to be our x-intercept. Is the graph tangent to the x-axis, or does it cross the x-axis at each x-intercept? Well, it may not be readily apparent, but right here, when you have an inflection point like this, the graph is actually tangent to the x-axis, even though the graph does cross the x-axis. When it gets into calculus, we find the first derivative for x equals 0, and we'll find that the slope at that point is going to be 0. So that'll be a horizontal tangent line where x equals 0. So that's getting into calculus language. But let's go here. Let's graph tangent. Yes, tangent. Tangent and crosses. Crosses where x equals 0. How many turning points does the graph have? Well, if we just look at our graph here, there are no turning points. So our answer to this question is none. Because we're not going from increasing to decreasing, or from decreasing to increasing. How many global maximum values? There are no maximum values. We have none. Or no local. We haven't even talked about that. So none. There'll be no global. And none local. And I haven't even talked about what those are yet. So, how many global minimum maximum values? How many local? None anywhere. Just flat out none. So now we have the second column, f of x equals x squared times 20x minus 2. So let's go ahead and put that back in. So x squared times 20x minus 2. And you can really just then you have to put a sign there, an operation between the graph, and that's what the things will look like. So we are starting from going up from -3, touching the x-axis at x equals 0, coming back down, and then crossing the x-axis where x equals 2. That's what's going on here. Let's go ahead and write that down. How many distinct factors does it have? Well, you have x squared, which is x times x. That's 1. And then we have the factor is going to be also, we have this one, x minus 2. So we have 2 distinct factors. And where are the graphs x-intercepts? Well, we have one at 0, 0, and we have another at 2, 0. Is the graph tangent to the x-axis, or does it cross the x-axis of each x-intercept? Well, we will say, looks like, let's look at this. The graph is tangent at x equals 0, but crosses at x equals 2. I don't know if you know too much about what tangent is yet, but we'll say tangent where x equals 0, and we'll say crosses where x equals 2. Next, how many turning points does the graph have? Let's look at our graph. We have a turning point where the graph is going from increasing to decreasing at x equals 0. And then we're going from decreasing to increasing here about where x equals 1. So this means we have 2 turning points. So we will say 2. How many global maximum values? Well, we do not have a global maximum value because our range is still going to be all real numbers. So none global, but these 2 turning points mean that we have 2 local. So they're not the absolute, not the highest high or the lowest low of the entire function, but they are local. Any place you have a peak or a valley, that means we have a local maximum value. We just have one local maximum value, right? Because the maximum is going to be a peak. So where x equals 0, we have a maximum value. So we have 1 global, a 1 local max. How many global minimum values? None. How many local minimum values? Minimum value over here where x equals about 1. So we have 1 local minimum value. And next we have this final column, x times 20x minus 2 and 20x plus 2. So let's go ahead and put that in the calculator. So get back to our function editor. I'm sure I remember that correctly. X minus 2. X minus 2, x plus 2. Oops. So common in. It's supposed to be parentheses. There we go. X plus 2. Here we graph this function. And we have how many turning points do we have? Looks like we have 2 turning points. Right? Let's go ahead and put down what that is. So how many distinct factors? We have 3. We have x, we have x minus 2, we have x plus 2. Where are the graphs x-intercepts? Well, we have x-intercepts where at -2, 0, at 0, 0, and at 2, 0. There we go. Is the graph tangent to the x-axis, or is it cross the x-axis at each x-intercept? And we are crossing at each x-intercept. It crosses. Let's say it crosses at each x-intercept. Okay, how many turning points does the graph have? Okay, same as column left, 2. How many global maximum values does it have? Well, we have no global maximum, but we have 1 local maximum. And down here, minimums, no global, but we have 1 local. So that's just some analysis on these 3 types of functions. So we're going to, we have this B, use graphic calculator, and we're getting some more varieties. I'm going to skip these. Here we have an x to the 4th power type situation. Just in the interest of brevity, I'm going to skip that. Now, the only thing you're going to have for these that's different, you're going to have a function that starts high and then does something that ends high. So for these, our range is going to be limited to, there's going to be a minimum value. But I don't want to go into the details of that. You might do that in class. And reflect. And here. Sketching graph. Explain what sketching graph of polynomial functions in intercept form. And here we have this one, example 1, sketch the graph of a polynomial function. Now we're going to go into much more detail in class, but when you multiply everything out here for this one, x times 1x plus 2 times 1x minus 3, you are going to get x cubed, and then at the last, you're going to get negative, well, x times 2 times negative 3, so you get negative 6x, and then stuff in between. And we can get more detail into this. What is it going to be exactly? You have to multiply these 2 together, then x. So if you go like this, you go to classes where you have x minus 3, x plus 2, so you get x squared, minus 3x. And then we have x times 2, 2x. And then we have negative 6. So what we have is, put down here, x times x squared minus x minus 6. And that's going to be equal to distributing the x to all these terms here. We have x cubed minus x squared and then we'll have minus 6x. So that's what that looks like. Identify the end behavior. Well, we have an odd-natured one. So as x approaches positive 30, and as far as graphing, we have an odd behavior function, and we have positive. And so our x-intercepts here are going to be, if we solve this, we're going to have x is equal to 0. So 0 is an x-intercept. We have x plus 2, our second factor, is equal to 0. So solving for this factor, we have a 0 of x is equal to negative 2. So x is equal to negative 2. That's one of our zeros. And our last one, we have this x minus 3 is equal to 0. If we add 3, we have x is equal to 3. So we put over here x is equal to 3. And we have odd. We're going to start low and end high as x approaches infinity. F of x approaches infinity. As f of x approaches negative infinity, f of x approaches negative infinity. What we're going to do is we're going to start. Use red here. Start from negative infinity, come up, and go down, touch the x-axis. We're going to come way down here, and then go up toward positive infinity. So that's basically what the sketch is going to look like. And we're going to do several more of these in this section. And we really get into this a lot more detail in pre-calculus. Good luck, as always. Thanks for being here.